everyone, this is AP Stats 4.2 Part 2. So trying to break these up into smaller parts. So in this one, we're going to look at a confounding variable where we left off on the last one. So this is an example, and it is asking us to come up with confounding variables. So in example 2, it says establish clearly why such a study cannot establish cause and effect. Suggest another variable that may be a confounding variable. Okay, so in the first one it says, teenagers who eat with their families at least 5 times per week are more likely to get better grades in school. So what are they trying to prove? They're trying to prove that kids who eat dinner, so I'm just shorthanding it here, kids that eat dinner at home get better grades, right? That somehow eating dinner gets better grades. Well, is it really the eating the dinner together that's getting the grades, or is there something else? So maybe, what else could it be? The kids are getting higher grades and they just happen to be eating dinner more often at home. Well, maybe they have less working parents or less numbers of jobs that working parents are doing. So that makes it less stressful for them at home. They have more access to extra help. Maybe the student is not in a sport, and that leads it easier for them to eat dinner at home and easier to have more time to study and to do better, right? Or extracurricular obligations, right? So any of that could have been a confounding factor. Next one. It says children enrolled in full-time daycares are more aggressive than other children. So what are they trying to do here? They're trying to say that daycares, kids that are in daycares, are more likely to be aggressive. So is it the daycare centers that are making them aggressive, or could there be a confounding variable? Well, maybe some of the variables could be the lack of attention that the kid is getting. So lack of attention, maybe it's that. Maybe it's less personal space makes them more aggressive. It's not necessarily the daycare itself of them just being in daycare. Maybe they just have less personal space and they're more used to a quiet environment. Okay, noise, right? Maybe it's just the noise that's making them more aggressive. So it's hard to say that's directly to childcare. Next one. Students that come from homes where there's at least 2 other siblings have healthier weights than single children. So what they're trying to say is that multiple siblings lead to healthy weight. So that's all we need is have more children and your kids will be healthier weights. Is that really what's going on there? Is it the number of children is really what's determining the healthy weights? Maybe it's something else. Maybe they have to fight a little bit for food, right? The bigger the family, the more once everybody says, let's go eat, that they go and grab food off the table. So maybe that's making them healthier because there's not as much to grab because they're sharing it more. Maybe they have more people. They have more siblings. Here's my symbol for people. Maybe they have more people to play with and be active with. Maybe that's leading to them be healthier, and it's not so much just the siblings itself. It's the idea that they're doing more activity. Maybe it's more likely for them not to eat fast food because large families usually can't afford to eat out as much. So maybe it's fast food, right? So no fast food or less fast food. Okay, so it's hard to say that's actually the having the multiple siblings is what's leading to the healthier weights. All right, and our last example, it says greenhouses cause flowers to grow faster than those that are not grown in a greenhouse. So somehow this object, this building, greenhouses, are causing the flowers to grow faster. Grow faster. Is that really it? Is it actually the building, the greenhouse themselves, or is there maybe something else? Well, maybe it doesn't have anything to do with that. Maybe the greenhouse is better at controlling humidity. So maybe it has more to do with the humidity than it actually does the box, that we could be just as good as the greenhouse structure if we just manage the humidity better. Maybe it has something to do with the water schedule or the sun schedule or the fertilizer schedule, right? It doesn't automatically mean that it's the actual greenhouse itself that is causing the flowers to grow faster. So that's our idea on a whole bunch of confounding variables for you to look at. Next part we're going to go into is how do we actually experiment well? So now we're getting down to the nut and bolts of how do you actually do this. So in an experiment, there's going to be some experimental units who are going to receive one treatment, and hopefully similar units are going to receive a different treatment. It is acceptable for there to be more than 2 treatments. You can have them broken up into groups of 4, 5, 10, 100. All of that is okay. We need to at least start with 2 to compare, 2 different groups. Okay? If groups vary too much, bias happens, right? If we have one group that's all older and one group that's all younger, there's going to be a bias there. There's going to be something that age difference is going to affect the results more than what it is we're trying to test. So the fix for bias. Anytime we think that there might be a bias, the way to get around that is to do random assignment. So we talked about how to randomly assign things in surveys where we are using random number generators, we were using the HAP method, we were using a table of values, a table of random numbers, maybe we were even using, we could use flipping a coin to decide, right? Anything like that where you're bringing in true randomness into the effect. Okay, sometimes it's even just the people who are deciding and you're doing something unconsciously. Maybe as you're trying to decide who goes into which group, the one that makes eye contact you tend to put into this side and the one who doesn't tends to go on this side. Maybe the one that smiles goes on this side and the one that seems grumpy goes on the other side. Well, that might affect all of the results. So we want to stay out of it. We don't want to be the ones who choose just by looking at somebody. We want it to be totally random where nobody can question me having a bias and potentially putting people that are similar in a group or in a different group. The random assignment means that the experimental units are assigned to treatments using some kind of chance process. And that's the ones that we talked about, the random number generator, picking from a hat, flipping a coin tables. So let's go through what a kind of like a flow chart of what it looks like. So we have our experimental units, right? These are our people, right? And then they're going to go and have some kind of treatment. They're going to take a pill, they're going to do an exercise, they're going to do something. We're going to mess with them somehow, right? And then at the end, we're going to measure their response. Okay, so what can we measure at the end? So this is some number to compare or something else. So this is the main process, but it really doesn't explain it as well as the next one I'm going to draw for you. So we're going to still start with experimental units. So I'm going to still do this one. Okay, and then we are going to do random assignment. So once we get our people, we're going to go through this idea of random assignment. I'm going to make it its own box. Okay, so this is as the people are coming in, we tell them to line up over here, take a number, put their name on a piece of paper, whatever that is to create the random assignment. And let's say we're going to test 2 groups, the ones that take or do exercise and the ones that don't. Well, then I need to separate them out using random assignment into 2 groups. So the first group is going to be treatment 1. So this might be the one who gets exercise. And then treatment 2 is the one with no exercise. And I'm making sure that they get assigned to these 2 groups totally randomly. That's the key part in experimental design. Okay, and then after that, they're each going to have their own response variable, whatever their blood pressure is at the end, whatever their weight is at the end. So this is going to be response variable 1. This is going to be response variable 2. So we're going to get some kind of data to take out to compare and to average for all the people who came out of treatment 1, the average of all the people who came out of treatment 2. And then the last step is we compare the results. And if there is a significant difference between them, then we say that that thing that we were testing, that treatment where they were going into 2 different treatments, is the thing that's making the biggest difference. Okay. All right, so what are the big elements of experimental design? There's 4 main components to it. And you're going to see a lot of these have been repeated in other stuff that we've used in vocabulary above. So the first big thing is you have to have comparison. You can't have just one group all do the same thing and then say, see, it helped. You have to be able to describe and define 2 different groups, one that has it, one that doesn't, one that has a higher dose, one that has a lesser dose. Somehow or another, you have to compare at least 2 different groups. Remember, that's 2 or more. It doesn't have to be exactly 2. Next one is the one we were just talking about. We have to have random assignment for it to be a good experimental design. Random assignment. Now, in surveys, we talked a lot about how to get the participants randomly. We're not talking about getting them. We already have them at this point. We're just trying to make sure they get randomly assigned to their treatment groups. Okay, third element of good design is going to be control. Now, control is one of those words that we say, oh, I know what that means, but let's go over what it actually means. It says you try to keep other variables that might affect the response the same. Okay, this is really difficult to do with humans. If they were something like a rat or a flower, we could put them in the same soil, give them the same amount of light, the same amount of water, and all we're really testing is fertilizer. Right? So control means we control everything else about their life except for the one thing we're testing. Well, humans don't work that way. We don't like to be locked up in little cages and shown the same amount of light and given the same amount of amusement and like all of that. We don't do that very well. So when we're talking control, especially with humans, we're going to just try to do whatever it is that we're testing. We're going to give them some guidelines and ask them to follow it, but we're not going to be able to like lock them up in little cages and make sure that every other element of their life is the same to only test the one thing. Humans just don't do that well with that. So I'm going to put in parentheses, lock them up. Here is the idea that if we could, we would. Humans, we're not going to do this to. Plants, some small animals, we can probably do that too. But humans, we aren't able to do absolutely everything, but we try to manage as much as we can, to control as much as we can. And then the last one is replication. I can't take two friends, put one randomly in one treatment group and one randomly in the other and say, see, look, this really worked. One person is not enough for us to say it worked. We go back into all of that, what was the confounding variables between those. So we want to make sure with the bigger groups, the better. The more people that we can randomly assign to the 2 or more treatment groups, the more likely it is that our average result at the end is showing the difference of the thing we're trying to test. So more people, better. That's what replication means. It means more people. Okay, so more is better. More numbers is better. Okay, and it says, so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. I agree. So if the treatments are assigned, and that's really the only thing we have to make sure of, completely by chance, random chance, we can call this a completely randomized design. And as long as we're doing random assignment by pure chance, we can do cause and effect. So keeping track of doing all of these good things along with our data, we get to call it a completely randomized design, and we get to go to cause and effect or causation. Last thing we're going to do is this one. All right, so this one says, some experiments may include blank that receives an inactive treatment or an existing baseline treatment. So you might have heard this phrase before. This is a control group. That is not the same thing as a good experimental design, even though they both have the word control. This is a control group. This is the people who get the sugar pill or the pill that looks like what everybody else is doing, is taking, smells like whatever everybody else is taking, but really doesn't have any active ingredients. If we're testing a lotion with medicine in it, the group that is being tested gets the medicine, the other one gets the same exact lotion without the medicine in it, and they have no idea who is getting which. That is a control group. Control group is the group that doesn't get the active ingredient. So I'm going to put up here so that you don't make the mistake. This is not the same as principle of design. We're using the word control differently here. Example 3, it says use principles of good experimental design to explain how you would carry out an experiment to see if a new exercise program improves the speed of sprinters. Okay, so basically what they're asking me to do is, does this exercise program change the speed? Okay, that's what I'm looking to set up. Now we can do everything else we did in part 1 about who is the experimental units, who is the response variables, what are the treatments and all of that. They're just asking me to explain those 4 principles of experimental design here. So that's going to be the main thing I'm going to work on right here. So let's start out with our first one, which was comparison. What are we comparing? So we are going to compare the speed of sprinters that use existing versus new exercise program. Okay, so one group is going to keep the program we've been doing all along, the other one is going to try the new one. We'll see if the speeds change any. Okay, next one is random assignment. How do I make sure they randomly go into different groups? So they said we have 68 students. So we would really want to have 34 in each group. So here's where I go back to the random number generator or the slips of paper. So if I want to do random assignment, I'm going to put all their names on slips of paper, put them into a hat, slips of paper in a hat, mix, and then I want to pick out 34 of them. So I'm just going to go in a handful and just start counting. 34 of them. Those 34 are going to get the new one, new exercise, and the remaining 34 keep the old one. Okay, so this is random chance. All right, next one is control. How am I going to do a control to this group, right? What I really love them to do is to do everything else the same. Eat the same amount of food, stay inside the same amount, get the same amount of sunlight, right? Whatever I could drink the same amount of water. But these are humans, it's going to be harder to do that. So probably the best I'm going to get away with is relating to this new exercise program. So I'm going to tell them, let's see, I'm going to give them maybe cards. So I'm going to give students cards describing their exercise program, and I'm going to ask them to stick to that and ask them to do only the exercises on the card, no more, no less. And then we'd probably say something about try to keep everything else the same as much as possible. Right, so we don't want, a few people in one of the group to suddenly decide this is the great time to start counting calories and what they eat, or bring on another spinning class or something stupid, right? We want them to try to stay the same. So we basically tell them, don't change anything else, just change this exercise for us. So we just ask them to not change anything else. And then the last one, where the heck am I going to fit replication? I'll put it over here. Replication. So replication is just me saying I've got enough in each group to handle any variability. So I'm going to say it was repeated 34 times in each group. Wow, I'm running out of room. Okay, repeated 34 times in each group. Okay, so we just did that. Those are our 4 design features. The response of a dummy treatment is called a placebo, the placebo. Now, if we're going to change this just a little bit, we're going to call it a placebo, and I'm going to add the word effect to this. So when you give somebody something that looks exactly the same, but it isn't the same, but it looks the same, tastes the same, right? That's our control group. If we're giving everybody a pill, we have to give them a pill so that they don't know that they're not getting the real treatment. So we call that a placebo. That is a placebo. But there's also something called a placebo effect, which has already been proven and seen many, many times, which is people who think they are getting the actual medicine sometimes do better overall just by thinking they do better. So when I compare those 2 numbers at the end, often we'll see both groups improve because one group thinks they're actually in the one that's getting the treatment, the real treatment, and for some reason, just that belief system leads them to do better anyway. So that's called the placebo effect. Other vocabulary words that we're going to do is, what's it called? When neither of the subjects nor those who gave them the medicine or the treatment know who is getting which treatment, the placebo or the regular one. This is called a double blind. There's also single blind. This is double blind. So double blind experiment. So this means that both the person taking the medicine and the person giving the medicine doesn't really know which one is the placebo and which one isn't. That keeps, again, either party from tipping the other party off unintentionally just by body language or smiling when they give them the treatment that's supposed to make them feel better, frowning when they're giving them the treatment that's going to make them hurt. Right? So we take that out of the 2, we make it double blind so that neither group knows. Somebody else knows, somebody else has the table or the clipboard that says this person is getting this, but the 2 people who are interacting during that treatment process, neither of them know which one is which. All right, and then a few last thoughts. We hope the difference of spread responses are so large that it's unlikely to happen by pure chance variation alone. So we're going to use some probability to do this at the end, and we're going to say, hey, this result is really unlikely. It's this % chance possible to happen by just pure chance, so we really think this medicine was really working. If the treatment effects are larger than we would expect, we call them statistically significant. So when it's more than just chance alone and we're seeing a response or a reaction to something, we're going to call that statistically significant. And statistically significant, when it comes from a well-designed experiment, does imply causation. All right, that's it. We'll see you for the next one.